So my science fair project was determining the ideal method of producing a supercavitating device. So what is supercavitation? So traditionally, underwater devices travel at slow speeds, and intuitively, inducing an air bubble around an object would reduce drag. And producing a fully formed air cavity is called supercavitation. And as shown in this graph right here, the drag of water versus air, water is exponentially higher, especially as the speed increases. And here here's a diagram of supercavitation. And supercavitation was first experimented on by German scientists in the 1940s, and later researched in the 1950s and 1960s in Russia for military uses. And this diagram, or this picture here, shows the early system used to experiment on supercavitation. So currently what is known is that there's a high importance on the size of the air bubble. A flat cavitator proves efficient, and what a flat cavitator is the front end of the supercavitation device, which releases air. And the front half of the air cavity is most stable. And the ideal width to length ratio is between 6:1 to 8:1. Current issues associated with supercavitation is an overall inefficient air cavity. A pulsating effect occurs. So basically, it can get caught in a pulsating effect in which the water comes in contact with the outer exterior of the device, such as a submarine. And currently traveling medium to long distances is not feasible. Now this project seeks to determine the feasibility of implementing an external rotational aspect and longitudinal air vents on the exterior to reduce drag and potentially solve the issues currently associated with supercavitation. And this is a sketch showing the overall design of the supercavitating device. And the length is 30 inches and the width is 4 inches. And here's an interior view showing the pneumatic system, which releases air and induces an air bubble, and also the 3 G-class engines. And then for testing, 3 trials are taken in a minimum runway length of 50 meters in a lake. And a launch pad is used, or like a launch ramp is used to launch the submarine or the device. And then these two, this shows the external supercavitation device and the interior pneumatic system. And for this project, the design was reviewed by a qualified scientist, and there's proper guidance during testing. And the strength of this project is a relatively large space to test, which is a lake. And with this design method, or this experiment design, the speed can be calculated, in which in a underwater chamber it can be more difficult to calculate. And the weaknesses are an inability to thoroughly examine air cavity and shape, which can be done in a water chamber, and then the cost as well, and the time restriction. So currently, supercavitation remains a difficult technology with multiple engineering challenges. And if made feasible, there are many potential widespread applications, especially in military use and possible commercial use, for example, traveling or transportation of goods. And for the unexpected outcomes and issues, the brass pneumatic fittings leak due to an absence of Loctite solutions to prevent air leakage. And I also figured out that it required a battery with a higher amperage output to power the solenoid valve, because the solenoid required a high amperage to release airflow at high PSIs. So we can only release with our lower amperage battery only 70 PSIs worth of air. And also, this goes in hand with the circuit board, which needed higher electricity tolerance.